IoT. The future is here with IoT. From smart homes to wearable tech, everything is connected and at our fingertips. But what exactly is IoT and how is it changing the way we live? Let's dive in and explore the endless possibilities of this game-changing technology. Are you ready to join the IoT revolution? Applications of IoT. The power of IoT lies in its applications. From healthcare to agriculture, IoT is revolutionizing the way industries operate. With the ability to collect and analyze data in real time, IoT is unlocking new possibilities and driving innovation. What is IoT? A world where everything is online and communicating to other things and to enhance people's lives is collectively known as Internet of Things. Genesis of IoT. The IoT started between the years 2008 and 2009. IoT is invented by Kevin Ashton. This picture represents evolutionary phases of Internet.
Digitalization and IoT. It means the IoT platform that enables the digitization of physical products and the collection of their data, also provides the digital link between a company and its products and customers. As we move towards a more connected world, the role of IoT in digitalization is becoming increasingly important. From smart homes to industrial automation, IoT is driving the digital transformation of various industries. With the ability to collect and analyze real-time data, IoT is enabling businesses to make informed decisions and improve their operations. IoT and its impact. Revolutionizing the way we live and work. From healthcare to agriculture, transportation to manufacturing, IoT is transforming every industry it touches. With the ability to connect devices, collect data, and automate processes, IoT is improving efficiency, reducing costs, and enhancing the customer experience. But the impact of IoT goes beyond just business. It's also improving our quality of life by making our homes more comfortable, our cities more livable, and our environment more sustainable. Projections on potential impact of IoT are impressive. About 14 billion, or just 0.06% of all things are connected to the internet today. Connected roadways. The future of transportation is now. With the rise of IoT, the dream of connected roadways is becoming a reality. Smart traffic management systems, intelligent transportation systems, and vehicle-to-vehicle communication are just a few examples of how IoT is revolutionizing the way we move. Connected roadways are not only improving traffic flow and reducing accidents, but they're also enabling greener and more sustainable transportation options. The connected factory. Revolutionizing manufacturing with IoT. The connected factory is the future of manufacturing, and it's already here. With IoT, factories can now connect all their assets, from machines to sensors to workers, to create a fully integrated system. This means real-time monitoring, predictive maintenance, and data-driven decision-making. The result? Increased efficiency, reduced downtime, and improved quality control. Connected factories are not only transforming the way we manufacture things, but they're also enabling new business models and revenue streams. Smart connected buildings. The future of sustainable living. With the rise of smart connected buildings, we're moving towards a more sustainable and energy-efficient future. These buildings are equipped with IoT sensors and systems that monitor and optimize energy usage, temperature control, and lighting. They also provide a seamless user experience, with features like smart locks, digital signage, and personalized climate control. Smart connected buildings not only reduce energy costs and carbon footprint, but they also improve occupant health and productivity. Building the future with a framework for digital ceilings. The digital ceiling is the next big thing in building automation, and it's here to revolutionize the way we manage our buildings. A framework for digital ceilings will enable us to integrate various IoT devices and systems, such as lighting, HVAC, security, and audio-visual, into a single platform. This will not only simplify building operations but also occupant experience and productivity. With a digital ceiling framework, we can also leverage data analytics and machine learning to optimize building performance and energy usage. The future of building automation is bright, and a digital ceiling framework is the first step towards achieving it.
Communications criteria. The characteristics and attributes you should consider when selecting and dealing with connecting smart objects. Range, frequency bands, power consumption, topology, constrained devices, constrained node networks. Range. How far does the signal need to be propagated? Short range. The classical wired example is a serial cable. Wireless technology that supports maximum of 10 meters between two devices. Medium range. In the range of tens to hundreds of meters, maximum distance is generally less than 1 mile between two devices. Examples of medium-range wireless technologies include IEEE 802.11 Wi-Fi. Wired technologies such as IEEE 802.3 Ethernet. Long range. Distances greater than 1 mile between two devices require long-range technologies. Wireless examples are cellular, 2G, 3G, 4G. Frequency bands. A frequency band is an interval in the frequency domain, delimited by a lower frequency and an upper frequency. Focusing on IoT access technologies, the frequency bands leveraged by wireless communications are split between licensed and unlicensed bands. Licensed spectrum is generally applicable to IoT long-range access technologies. Users must subscribe to the services when connecting their IoT devices. Sell better guarantee of services. Unlicensed spectrum are used in many communications technologies for short-range devices, SRDs. Free and open for anyone to use. No guarantees or protections are offered. Powered nodes and battery-powered nodes. A powered node has a direct connection to a power source, and communications are usually not limited by power consumption criteria. Battery-powered nodes bring much more flexibility to IoT devices. These nodes are often classified by the required lifetimes of their batteries. For battery-powered nodes, IoT wireless access technologies must address the needs of low power consumption and connectivity. A new wireless environment known as Low Power Wide Area, LPWA. Low Power Wide Area, LPWA, technologies are therefore ideal for battery-powered IoT sensors. Topology. Among the access technologies available for connecting IoT devices, three main topology schemes are dominant: star, mesh, and peer-to-peer. Star topologies utilize a single central base station or controller to allow communications with endpoints. For long-range and short-range technologies, a star topology is prevalent. In a mesh topology, every device is connected to another device via a particular channel. Peer-to-peer topologies allow any device to communicate with any other device as long as they are in range of each other. For medium-range technologies, a star, peer-to-peer, or mesh topology is common. The constrained devices are end nodes with sensors/actuators that can handle a specific application purpose. They are usually connected to gateway-like devices, low-power lossy network, and in turn communicates with the IoT cloud platforms. The constrained devices are classified into three categories as shown in the table below. Constrained node networks. Constrained node networks are often referred to as low-power and lossy networks, LLNs. Low-power, battery-powered constraints. Lossy network performance may suffer from interference and variability due to harsh radio environments. Protocols that can be used for constrained node networks must be evaluated in the context of the following characteristics: data rate and throughput, latency and determinism.
UNIT3 IP as a IoT network layer. Topics covered. From 6LoWPAN to 6Low. Header compression. Fragmentation. Profiles and compliances. Header compression. 6LoWPAN header compression is stateless, and conceptually it is not too complicated. However, a number of factors affect the amount of compression, such as implementation of IFC 4944 versus IFC 6922, whether UDP is included, and various IPv6 addressing scenarios. It is beyond the scope of this book to cover every use case and how the header fields change for each. However, this chapter provides an example that shows the impact of 6-low-pan header compression. Fragmentation. The fragment header utilized by 6-low-pan is composed of three primary fields: datagram size, datagram tag, and datagram offset. The 1-byte datagram size field specifies the total size of the unfragmented payload. Datagram tag identifies the set of fragments for a payload. Finally, the datagram offset field delineates how far into a payload a particular fragment occurs. Figure 5-5 provides an overview of a 6-low-pan fragmentation header. Mesh addressing. The purpose of the 6-low-pan mesh addressing function is to forward packets over multiple hops. Three fields are defined for this header: hop limit, source address, and destination address. Analogous to the IPv6 hop limit field, the hop limit for mesh addressing also provides an upper limit on how many times the frame can be forwarded. Each hop decrements this value by 1 as it is forwarded. Once the value hits 0, it is dropped and no longer forwarded. The source address and destination address fields for mesh addressing are IEEE 802.15.4 addresses indicating the endpoints of an IP hop. Figure 5-6 details the 6-low-pan mesh addressing header fields. Profiles and compliances. As discussed throughout this chapter, leveraging the Internet Protocol Suite for smart objects involves a collection of protocols and options that must work in coordination with lower and upper layers. Therefore, profile definitions, certifications, and promotion by alliances can help implementers develop solutions that guarantee interoperability and/or interchangeability of devices. This section introduces some of the main industry organizations working on profile definitions and certifications for IoT-constrained nodes and networks. You can find various documents and promotions from these organizations in the IoT space, so it is worth being familiar with them and their goals. Internet Protocol for Smart Objects, IPSO, Alliance. Established in 2008, the Internet Protocol for Smart Objects, IPSO, Alliance has had its objective evolve over years. The Alliance initially focused on promoting IP as the premier solution for smart objects communications. Today, it is more focused on how to use IP, with the IPSO Alliance organizing interoperability tests between Alliance members to validate that IP for smart objects can work together and properly implement industry standards. The IPSO Alliance does not define technologies, as that is the role of the IETF and other standard organizations, but it documents the use of IP-based technologies for various IoT use cases and participates in educating the industry. Plus or minus, as the IPSO Alliance declares in its value and mission statement, it wants to ensure that engineers and product builders will have access to the necessary tools for how to build the IoT right. For more information on the IPSO Alliance, visit www.ipso Alliance. Y-Sun Alliance. The Y-Sun Alliance is an example of efforts from the industry to define a communication profile that applies to specific physical and data link layer protocols. Currently, Y-Sun's main focus is on the IEEE 802.15.4 grams protocol and its support for multi-service and secure IPv6 communications with applications running over the UDP transport layer. The utilities industry is the main area of focus for the Y-Sun Alliance. The Y-Sun Field Area Network, FAN, profile enables smart utility networks to provide resilient, secure, and cost-effective connectivity with extremely good coverage in a range of topographic environments, from dense urban neighborhoods to rural areas. Thread. A group of companies involved with smart object solutions for consumers created the Thread Group. This group has defined an IPv6-based wireless profile that provides the best way to connect more than 250 devices into a low-power, wireless mesh network. The wireless technology used by Thread is IEEE 802.15.4, which is different from Wi-Sun's IEEE 802.15.4 grams. IPv6 Ready logo. Initially, the IPv6 Forum ensured the promotion of IPv6 around the world. Once IPv6 implementations became widely available, the need for interoperability and certification led to the creation of the IPv6 Ready Logo program. The IPv6 Ready Logo program has established conformance and interoperability testing programs with the intent of increasing user confidence when implementing IPv6. The IPv6 core and specific IPv6 components, such as DHCP, IPsec, and Customer Edge Router certifications, are in place. Plus or minus, these certifications have industry-wide recognition, and many products are already certified. An IPv6 certification effort specific to IoT is currently under definition for the program. IoT Application Layer Protocols. When considering constrained networks and/or a large-scale deployment of constrained nodes, verbose web-based and data model protocols, as discussed in the previous section, may be too heavy for IoT applications. To address this problem, the IoT industry is working on new lightweight protocols that are better suited to large numbers of constrained nodes and networks. Two of the most popular protocols are COAP and MQTT. Figure 6-6 highlights their position in a common IoT protocol stack. COAP, Constrained Application Protocol, COAP, resulted from the IETF Constrained Restful Environments, CORE, working group's efforts to develop a generic framework for resource-oriented applications targeting constrained nodes and networks. The COAP framework defines simple and flexible ways to manipulate sensors and actuators for data or device management. The IETF Core Working Group has published multiple standards track specifications for COAP, including the following: Filled Square AFC 6690, Constrained Restful Environments, Core, Link Format Filled Square AFC 7252, the Constrained Application Protocol, COAP. RFC 7641, Observing Resources in the Constrained Application Protocol, COAP. RFC 7959, Blockwise Transfers in the Constrained Application, MQTT. Their research resulted in the development and implementation of the Message Queuing Telemetry Transport, MQTT, protocol that is now standardized by the Organization for the Advancement of Structured Information Standards, OASIS. An MQTT client can act as a publisher to send data, or resource information, to an MQTT server acting as an MQTT message broker. In the example illustrated in Figure 6-10, the MQTT client on the left side is a temperature, temp, and relative humidity, RH, sensor that publishes its temp, RH data. The MQTT server, or message broker, accepts the network connection along with application messages, such as temp, RH data, from the publishers. It also handles the subscription and unsubscription process and pushes the application data to MQTT clients acting as subscribers. The application on the right side of Figure 6-10 is an MQTT client that is a subscriber to the temp, RH data being generated by the publisher or sensor on the left. This model, where subscribers express a desire to receive information from publishers, is well known. A great example is the collaboration and social networking application Twitter. Compared to the COAP message format in Figure 6-7, you can see that MQTT contains a smaller header of 2 bytes compared to 4 bytes for COAP. The first MQTT field in the header is message type, which identifies the kind of MQTT packet within a message. 14 different types of control packets are specified in MQTT version 3.1.1. Each of them has a unique value that is coded into the message type field. Note that values 0 and 15 are reserved. MQTT message types are summarized in Table 6-2. Compared to the COAP message format, You can see that MQTT contains a smaller header of 2 bytes compared to 4 bytes for COAP. The first MQTT field in the header is message type, which identifies the kind of MQTT packet within a message. 14 different types of control packets are specified in MQTT version 3.1.1. Each of them has a unique value that is coded into the message type field. Note that values 0 and 15 are reserved. MQTT message types are summarized in Table 6-2. Thanks for watching.
An introduction to data analytics for IoT. In the world of IoT, the creation of massive amounts of data from sensors is common and one of the biggest challenges, not only from a transport perspective but also from a data management standpoint. Modern jet engines are fitted with thousands of sensors that generate a whopping 10 gigabytes of data per second. Analyzing this amount of data in the most efficient manner possible falls under the umbrella of data analytics. Structured versus unstructured data. Structured data and unstructured data are important classifications as they typically require different tool sets from a data analytics perspective. Structured data means that the data follows a model or schema that defines how the data is represented or organized, meaning it fits well with a traditional relational database management system, RDBMS. In many cases you will find structured data in a simple tabular form, for example, a spreadsheet where data occupies a specific cell and can be explicitly defined and referenced. Unstructured data lacks a logical schema for understanding and decoding the data through traditional programming means. Examples of this data type include text, speech, images, and video. As a general rule, any data that does not fit neatly into a predefined data model is classified as unstructured data. Data in motion versus data at rest. Data in IoT networks is either in transit, data in motion, or being held or stored, data at rest. Examples of data in motion include traditional client-server exchanges, such as web browsing and file transfers, and email. Data saved to a hard drive, storage array, or USB drive is data at rest. IoT Data Analytics Overview. The true importance of IoT data from smart objects is realized only when the analysis of the data leads to actionable business intelligence and insights. Data analysis is typically broken down by the types of results that are produced. 4 types of data analysis results. Descriptive. Descriptive data analysis tells you what is happening, either now or in the past. For example, a thermometer in a truck engine reports temperature values every second. From a descriptive analysis perspective, you can pull this data at any moment to gain insight into the current operating condition of the truck engine. If the temperature value is too high, then there may be a cooling problem or the engine may be experiencing too much load. Diagnostic. When you are interested in the why, diagnostic data analysis can provide the answer. Continuing with the example of the temperature sensor in the truck engine, you might wonder why the truck engine failed. Diagnostic analysis might show that the temperature of the engine was too high, and the engine overheated. Applying diagnostic analysis across the data generated by a wide range of smart objects can provide a clear picture of why a problem or an event occurred. Predictive. Predictive analysis aims to foretell problems or issues before they occur. For example, with historical values of temperatures for the truck engine, predictive analysis could provide an estimate on the remaining life of certain components in the engine. These components could then be proactively replaced before failure occurs. Or perhaps if temperature values of the truck engine start to rise slowly over time, this could indicate the need for an oil change or some other sort of engine cooling maintenance. Prescriptive. Prescriptive analysis goes a step beyond predictive and recommends solutions for upcoming problems. A prescriptive analysis of the temperature data from a truck engine might calculate various alternatives to cost-effectively maintain our truck. These calculations could range from the cost necessary for more frequent oil changes and cooling maintenance to installing new cooling equipment on the engine or upgrading to a lease on a model with a more powerful engine. Prescriptive analysis looks at a variety of factors and makes the appropriate recommendation. Both predictive and prescriptive analyses are more resource-intensive and increase complexity, but the value they provide is much greater than the value from descriptive and diagnostic analysis. Machine learning overview. Machine learning is, in fact, part of a larger set of technologies commonly grouped under the term artificial intelligence, AI. AI includes any technology that allows a computing system to mimic human intelligence using any technique, from very advanced logic to basic, if-then-else, decision loops. Any computer that uses rules to make decisions belong to this group. Supervised learning. In supervised learning, the machine is trained with input for which there is a known correct answer. For example, suppose that you are training a system to recognize when there is a human in a mine tunnel. A sensor equipped with a basic camera can capture shapes and return them to a computing system that is responsible for determining whether the shape is a human or something else, such as a vehicle, a pile of ore, a rock, a piece of wood, and so on. Unsupervised learning. In some cases, supervised learning is not the best method for a machine to help with a human decision. Suppose that you are processing IoT data from a factory, manufacturing small engines. You know that about 0.1% of the produced engines on average need adjustments to prevent later defects, and your task is to identify them before they get mounted into machines and shipped away from the factory. With hundreds of parts, it may be very difficult to detect the potential defects, and it is almost impossible to train a machine to recognize issues that may not be visible. Neural networks. Processing multiple dimensions requires a lot of computing power. It is also difficult to determine what parameters to input and what combined variations should raise red flags. Similarly, supervised learning is efficient only with a large training set. Larger training sets usually lead to higher accuracy in the prediction. Training the machines was often deemed too expensive and complicated. Neural networks are milliliter methods that mimic the way the human brain works. When you look at a human figure, multiple zones of your brain are activated to recognize colors, movements, facial expressions, and so on. Your brain combines these elements to conclude that the shape you are seeing is human. Neural networks mimic the same logic. The information goes through different algorithms, called units, each of which is in charge of processing an aspect of the information. Big data analytics tools and technology. Big data analytics can consist of many different software pieces that together collect, store, manipulate, and analyze all different data types. Generally, the industry looks to the 3 V's to categorize big data. Velocity refers to how quickly data is being collected and analyzed. Hadoop distributed file system is designed to ingest and process data very quickly. Smart objects can generate machine and sensor data at a very fast rate and require database or file systems capable of equally fast ingest functions. Variety refers to different types of data. Often you see data categorized as structured, semi-structured, or unstructured. Different database technologies may only be capable of accepting one of these types. Hadoop is able to collect and store all 3 types. Volume refers to the scale of the data. Typically, this is measured from gigabytes on the very low end to petabytes or even exabytes of data on the other extreme. The characteristics of big data can be defined by the sources and types of data. First is machine data, which is generated by IoT devices and is typically unstructured data. Second is transactional data, which is from sources that produce data from transactions on these systems, and have high volume and structured. Third is social data sources, which are typically high volume and structured. Fourth is enterprise data, which is data that is lower in volume and very structured. Hence, big data consists of data from all these separate sources. Hadoop. Hadoop is the most recent entrant into the data management market, but it is arguably the most popular choice as a data repository and processing engine. Hadoop was originally developed as a result of projects at Google and Yahoo. The original intent for Hadoop was to index millions of websites and quickly return search results for open-source search engines. Initially, the project had 2 key elements. Hadoop Distributed File System, HDFS. A system for storing data across multiple nodes. MapReduce. A distributed processing engine that splits a large task into smaller ones that can be run in parallel. Hadoop relies on a scale-out architecture that leverages local processing, memory, and storage to distribute tasks and provide a scalable storage system for data. Both MapReduce and HDFS take advantage of this distributed architecture to store and process massive amounts of data and are thus able to leverage resources from all nodes in the cluster. For HDFS, this capability is handled by specialized nodes in the cluster, including name nodes and data nodes. The Hadoop ecosystem. Since the initial release of Hadoop in 2011, many projects have been developed to add incremental functionality to Hadoop and have collectively become known as the Hadoop ecosystem. Apache Kafka, Apache Spark, Apache Storm and Apache Flink. Lambda architecture. Edge analytics core functions. To perform analytics at the edge, data needs to be viewed as real-time flows. Whereas big data analytics is focused on large quantities of data at rest, edge analytics continually processes streaming flows of data in motion. Streaming analytics at the edge can be broken down into three simple stages. Raw input data. Analytics processing unit, APU. Output streams. In order to perform analysis in real time, the APU needs to perform the following functions: filter, transform, time, correlate. Network analytics. Another form of analytics that is extremely important in managing IoT systems is network-based analytics. Network analytics is concerned with discovering patterns in the communication flows from a network traffic perspective. Network analytics has the power to analyze details of communications patterns made by protocols and correlate this across the network. It allows you to understand what should be considered normal behavior in a network and to quickly identify anomalies that suggest network problems due to suboptimal paths, intrusive malware, or excessive congestion. Contents. 1. Operating system in Raspberry Pi. 2. Configuring Raspberry Pi. 3. Programming Raspberry Pi with Python. Raspberry Pi is a popular single-board computer that can run various operating systems. The choice of the operating system depends on your specific requirements and the intended use of the Raspberry Pi. 1. Raspbian, now called Raspberry Pi OS. Raspbian is the official operating system for Raspberry Pi. 1. It is based on the Linux distribution Debian and is optimized for the Raspberry Pi hardware. 1. Raspberry Pi OS provides a user-friendly interface and comes with a wide range of pre-installed software. 2. Ubuntu. Ubuntu is a popular Linux distribution that has an official version optimized for Raspberry Pi called Ubuntu Mate. 2. It offers a full-fledged desktop environment and a variety of software packages available in the Ubuntu ecosystem. 3. Kali Linux. Kali Linux is a specialized Linux distribution designed for penetration testing, digital forensics, and network security assessments. 3. It can be useful for security professionals and enthusiasts who want to perform security-related tasks on their Raspberry Pi. Configuring a Raspberry Pi. It involves setting up the hardware, installing an operating system, and configuring various settings to suit your needs. Here is a general overview of the steps involved. 1. Hardware setup. Connect the Raspberry Pi board to a power source using a compatible power supply. Connect a keyboard, mouse, and display to the appropriate ports on the Raspberry Pi, if required. Insert a micro SD card into the card slot on the Raspberry Pi. This card will hold the operating system and data. 2. Operating system installation. Download the desired operating system for your Raspberry Pi, e.g., Raspberry Pi OS, from the official website. Use an SD card formatter tool to format the micro SD card. Use an image writing tool like Etcher to write the downloaded operating system image to the micro SD card. Once the image is written, insert the micro SD card into the Raspberry Pi. 3. Initial boot and setup. Connect the Raspberry Pi to a display and power it on. Follow the on-screen instructions to complete the initial setup, such as selecting language, keyboard layout, and setting passwords. 4. Post-installation configuration. Update the operating system by running the following commands in the terminal. Sudo apt update. Sudo apt upgrade. Configure the Raspberry Pi by accessing the configuration menu. Sudo raspi config. Here, you can change settings such as hostname, Wi-Fi network, GPU memory allocation, overclocking, and more. 5. Software installation and customization. Install additional software packages as per your requirements using the package manager, e.g., apt for Raspberry Pi OS. Sudo apt install package name. Customize your Raspberry Pi by exploring the available options and settings specific to your chosen operating system and applications. 6. Networking and remote access. Configure network settings, including Wi-Fi setup or Ethernet connection. Enable SSH, secure shell, for remote access to your Raspberry Pi if needed. Programming Raspberry Pi with Python. 1. Python is a popular choice due to the simplicity and versatility of the Python programming language. 1. Here are the steps to get started with programming Raspberry Pi using Python. 3. 1. 3. Install Python. Check if Python is already installed on your Raspberry Pi by running the following command in the terminal. Python, version. If Python is not installed, you can install it using the package manager by running sudo apt install python 3 Verify the installation by running python 3 version 1 2 1 Choose an integrated development environment IDE. You can use any text editor to write Python code, but using an IDE can enhance your development experience. Some popular Python IDEs for Raspberry Pi include Thorny, Idle, Gearny, and Pcharm. 1. 3. 1. Write and run Python code. Open your preferred IDE or text editor and create a new Python file with a py extension. Write your Python code in the file. For example, you can start with a simple, hello, world, program. Python. Print, hello, world. Save the file with a meaningful name, such as hello_world.py. Point 4. Run the Python code. Open a terminal and navigate to the directory where you saved the Python file. Run the Python code using the following command. Python 3 hello_world.py. The output, hello, world, should be displayed in the terminal. 5. Access Raspberry Pi hardware. Raspberry Pi offers various hardware interfaces and GPIO, general purpose input, output, pins that can be controlled with Python. Install the RPI. GPIO library to access GPIO pins. Run the following command to install it. Sudo apt install python 3 RPI, GPIO. Import the library in your Python code to control the GPIO pins. For example, Python. Import RPI. GPIO as GPIO. GPIO, set mode, GPIO, BCM. GPIO, setup, 18, GPIO, out. GPIO, output, 18, GPIO, high. 6. Explore Python libraries for Raspberry Pi. Raspberry Pi has a vast ecosystem of Python libraries and modules for various functionalities, such as sensors, displays, camera, and more. Some popular libraries include _pacamera for camera access, _SMBUS for I2C communication, _Adafruit_DHT for DHT temperature and humidity sensors, and pgame for game development. Import time. Import RPI. GPIO as GPIO. Hash pin definitions. LED_pin equals 12. Hash suppress warnings. GPIO, set warnings, false. Hash use, GPIO, pin numbering. GPIO, set mode, GPIO, BCM. Hash set LED pin as output. GPIO, setup, LED_pin, GPIO, out. Hash blink forever. While true. GPIO, output, LED_pin, GPIO, high, hash. Turn LED on. Time, sleep, 1, hash delay for 1 second. GPIO, output, LED_pin, GPIO, low, hash. Turn LED off. Time, sleep, 1, hash delay for 1 second. Thank you.
Contents. What is Raspberry Pi? Difference between Arduino and Raspberry. Basic Pi command line -1. Basic Pi command line2. Hardware layout. Hardware requirements. Raspberry Pi. Raspberry Pi is the name of a series of single-board computers made by the Raspberry Pi Foundation, a UK charity that aims to educate people in computing and create easier access to computing education. The Raspberry Pi launched in 2012, and there have been several iterations and variations released since then. The original Pi had a single-core 700 MHz CPU and just 256 MB RAM, and the latest model has a quad-core 1.4 GHz CPU with 1 GB RAM. The main price point for Raspberry Pi has always been $35, and all models have been $35 or less, including the Pi Zero, which costs just $5. Arduino is microcontroller, whereas Raspberry Pi is microcomputer. Microcontroller. A microcontroller is a compact integrated circuit, IC, that consists of a central processing unit, CPU, memory, both program memory and data memory, and input-output peripherals, all integrated onto a single chip. Microcontrollers are designed for specific tasks and embedded systems where they control and manage various functions. Microcontrollers are often programmed to interact with sensors, actuators, and other external devices to perform specific functions. They are optimized for low power consumption, real-time processing, and have a smaller footprint compared to microcomputers. Microcomputer. A microcomputer, also known as a personal computer, PC, is a complete computing system that consists of a microprocessor, memory, input-output devices, such as keyboard, mouse, and display, and other peripherals. Unlike microcontrollers, microcomputers are not limited to specific tasks or applications and are capable of running general-purpose operating systems and software applications. Microcomputers are commonly used by individuals for various purposes, such as office work, internet browsing, multimedia consumption, gaming, and more. Hardware layout. Raspi config. The Raspberry Pi configuration tool in Raspbin, allowing you to easily enable features such as the camera, and to change your specific settings such as keyboard layout. Config.txt. The Raspberry Pi configuration file. Wireless networking. Configuring your Pi to connect to a wireless network using the Raspberry Pi 3's or Pi Zero W's inbuilt wireless connectivity, or a USB wireless dongle. Wireless access point. Configuring your Pi as a wireless access point using the Raspberry Pi 3 and Pi Zero W's inbuilt wireless connectivity, or a USB wireless dongle.
Smart objects, the things in IoT. Smart objects, the things in IoT, sensors, actuators, and smart objects, sensor networks, connecting smart objects, communications criteria, IoT. Access, technologies. Sensors, actuators and smart objects. 1. A sensor, it senses. 2. More specifically, a sensor measures some physical quantity and converts that measurement reading into a digital representation. 3. Example, light sensors, thermostat sensor, pressure sensors, etc. Categories. Active or passive, sensors can be categorized based on whether they produce an energy output and typically require an external power supply. Active, or whether they simply receive energy and typically require no external power supply. Passive. Invasive or non-invasive, sensors can be categorized based on whether a sensor is part of the environment it is measuring, invasive, or external to it, non-invasive. Contact or no contact, sensors can be categorized based on whether they require physical contact with what they are measuring, contact, or not, no contact. Absolute or relative, sensors can be categorized based on whether they measure on an absolute scale, absolute, or based on a difference with a fixed or variable reference value, relative. Area of application, sensors can be categorized based on the specific industry or vertical where they are being used. How sensors measure, sensors can be categorized based on the physical mechanism used to measure sensory input. Precision agriculture, smart farming. 1. Which uses a variety of technical advances to improve the efficiency, sustainability, and profitability of traditional farming practices. 2. Biodegradable, passive microsensors to measure soil and crop and conditions. 3. These sensors, developed at North Dakota State University, NDSU, can be planted directly in the soil and left in the ground to biodegrade without any harm to soil quality. Actuators. 1. Actuators are natural complements to sensors. 2. Sensors provide the information, actuators provide the action. Actuators are classified based on 1. Type of motion. Actuators can be classified based on the type of motion they produce. For example, linear, rotary, 1/2/3 axes. 1. Power. Actuators can be classified based on their power output. For example, high power, low power, micro power. 2. Binary or continuous. Actuators can be classified based on the number of stable state outputs. 3. Area of application. Actuators can be classified based on the specific industry or vertical where they are used. 4. Type of energy. Actuators can be classified based on their energy type. MEMS micro-electromechanical system. 1. It is a technology used to do small integrated devices or systems that is a combination of mechanical and electrical components. 2. One of the keys to this technology is a microfabrication technique that is similar to what is used for microelectronic integrated circuits. 3. MEMS an attractive option for a huge number of IoT applications. 4. Smartphones also use MEMS technologies for things like accelerometers and gyroscopes. 5. Size can vary from a few micrometers to millimeters. 6. MEMS uses batch processing technologies. 7. Sensors such as MEMS accelerators, MEMS pressure sensors, tilt sensor and other types of sensors. 8. Actuators such as MEMS switches, micro pumps, micro levels and micro grippers.